Okay, so we've talked about the beams, the bending stress, uh, the bending force from using the moment diagram. We talked about the longitudinal and transverse shear from the shear diagrams. And we also even talked about how if you have an I-beam, you've got that approximation formula for finding the longitudinal and transverse shear. And we also talked about the transverse and longitudinal shear are equal, so we can just use the same formula to find each of them. We left off on Thursday with some homework on the transverse shear. Did you guys have any questions on that you wanted me to go over? Is that your way of saying you haven't even looked at it yet, pretty much, right? Okay. We can go over it more next class if we need to. Anyway, don't remember. It was a long Thanksgiving. That's understandable, no problem. So the thing we're going to look at today is actually what is the most common reason for a beam to fail in analysis, and that is deflection. What deflection is nothing more than it's a variation in vertical position. And to be more specific, it's a variation from the unloaded position to the loaded position. Now, if you think about it, if you have like a meter stick or whatever set across two supports, it sits there relatively straight. Now, it will sag just a little bit under its own weight, but if you put a book or something in the middle of it, of course, it's going to sag even more. That distance between where it was unloaded and where it was loaded, that is the deflection. Now, a beam technically could deflect a lot and not have any structural problems. Especially a large beam carrying a heavy load, it could sag 4 or 5 inches if it was a long enough span and really not have any structural issues. It would not fail for shear, would not fail for bending stress. It would be just fine. The problem is, in construction, when we're using this in a building, there are other systems that depend on those structural members, not just the support of the rest of the structure, not just the support of the building. You have mechanicals like your ductwork going through, holes drilled in your joist for the ductwork to go through. You have wires and plumbing going through there. If one spot is flexing 3 or 4 or even 1.5 inches or 2 inches, the ductwork's going to get kinked or bent or separate, or the plumbing's going to get bent or damaged. Wiring, probably not such a big deal, but you still don't want it being pulled and stretched a lot. Also, if you have a finished floor beneath it, if you have sheetrock or plaster on the ceiling below that, you can't have a whole lot of deflection, or that that sheetrock's going to crack all the pieces on you. And it's going to be really horrible looking. So because of that, we limit the deflection beyond what would be required as a limit for structural integrity. And that deflection is generally limited using the length divided by a factor. That factor typically is anywhere from 120 to 480. In your textbook, page 403 is a table describing those. I get to 403 here. Page 403. So you can see for different applications, roof beams. Typically, your roof beams are allowed to have a little bit more sag to them, a little bit more deflection. I mean, you can see you got L over 180 standard for live loads, L over 120 for your dead load. So you're saying the dead load can sag more because it's always there. You don't have to worry about the load ever being removed and it flexing back up. So you're not going to crack, the dead load is not going to cause any cracks in your sheetrock. So your dead load can have a larger sag. The smaller that number is on the bottom, the more you're allowed to deflect. They don't have anything listed as L over 480. Floor beams, ordinary usage for live load, it's L over 360 they're listing. If you have tile floors or any sort of a hard floor like that that is susceptible to cracking, you usually change that to an L over 480 so you don't crack the grout lines in your tiles and stuff like that. I have actually seen floors that flexed enough because it was not specified in the design stage that they wanted tile floors. Typically, I always tell people you put tile on concrete, tile on a wood frame floor. It must be specifically engineered for it. I've seen it actually crack the tile, a 12-inch tile, crack it down the middle because the floor flexed enough to cause that kind of stress on the tile. So your roof, like I said, gets a little bit more allowable flexure to it. You can see the plaster ceiling there bumps it up to an L360, so it limits your deflection a little bit more when you have the plaster ceiling. Floors are always usually pretty limited, and especially, like I said, the textbook doesn't talk about tiles, but if you're going to tiles, it'd be L over 480. So how does that work? Well, let's say I have a beam that spans 12 feet. First thing I have to do is convert that into inches. So that's 144 inches. And let's say that this is a roof beam, and it's being loaded commercial installation without plaster. So we're using an L over 240 condition. What that means is the allowable deflection is your length of 144 inches divided by 240. So that's 0.6 inches of deflection. So that beam can flex just between 1/2 and 5/8 of an inch before it's going to fail in deflection. This works well for reasonable beams. If you have longer beams, I'm going to say you got a 40-foot beam, and let's say this is a beam with a plaster ceiling, so we're going to use an L over 360 on it. Well, 40 feet is 480 inches. Even if you take that over 360, you're going to get 1 1/3 inches. So it's almost 1 3/8 inch that beam can sag. Now you think about that, the problems that can cause, even it's allowable, that would pass our analysis. But if you got it moving an inch and 1/4 to an inch and 3/8, especially if you get like a floor joist or something that's moving that way, and you get a single floor joist or a single floor truss that's moving that much, and the ones beside it are not, you know, that flexure can cause a lot of problems in a sheetrock ceiling down below, or like I said, in plumbing or ductwork. So that's why when we do floors especially, but we do it with roofs as well, but with floors it's even more important. Let's say you have your standard floor truss set up here. They usually attach, usually in spots like this at the lower part of a vertical web, they'll attach 2x4s. They call them strong backs. So if this is your trusses from the top, those 2x4s go like this. They hold them together so that one truss cannot sag on its own. That if one truss is sagging, it's allowed to go 1 1/4 inches. The other trusses beside it are going to flex and sag as well, so that it doesn't get that sudden movement right at one spot. Your floor sheeting also does a little bit to tie them together in that way, but it's still necessary to have those strong backs in there. Otherwise, it really wreaks havoc on your sheetrock down below. The other thing those strong backs also prevent is sideways buckling on your beams. It's possible for the beam to twist because it gets under so much load. It doesn't fail in bending, but it starts to twist a little bit, and that prevents that as well. If that ever happens, if you've ever seen a floor joist that has done that, especially if there's a finished basement underneath, it makes a mess. It rips the sheetrock, really rips slots in the sheetrock. It's horrible. So anyway, how do we then look at a beam and decide how much is going to flex? Well, there are a couple of ways we can go about it. If we have a simply supported beam, and let's say that this has a single point load on a 12-foot span, we'll give it a single point load of, I don't know, 12-foot span will go 3,000 pounds here. What we could do is figure out the radius. If we knew the shape of the beam, we could figure out the radius of curvature. So let's just do this. Let's say that this beam is a 4-inch by 10-inch beam, wood beam. Our elastic modulus, let's say, is, what do I use for E? Wood's typically like 1.7 to 1.9, so we'll do 1,700,000 for our elastic modulus, and we'll use, that's all we should need for now. We need to find the moment of inertia of that about the horizontal axis here. So that moment of inertia, the parallel dimension is the 4, perpendicular dimension is the 10, so that's 10 to the third over 12. So 4 times 10 to the third divided by 12. 333.33. So what we find is the radius of curvature would be equal to the elastic modulus times the moment of inertia over the moment in the moment from the moment diagram. Well, let's find the moment from the moment diagram. Pretty simple. The reactions here are each 1,500. Shear diagrams are up 1,500. Oops. Come on. Up to 1,500, over flat, down 3,000 to negative 1,500 and back up. So this is just 1,500 times 6 feet. So on the moment diagram, it's just going to be a triangle like that. 1,500 times 6 feet is 9,000 foot-pounds. So M is 9,000 foot-pounds. So E, 1,700,000 times I of 333.33 over 9,000 foot-pounds, but elastic modulus and moment of inertia are always in inches. So we're going to change that 9,000 inches, which is 108,000 inch-pounds. So our radius of curvature, 1,700,000. Oops, I did that wrong. Times 333.33 divided by 108,000. I realize I'm missing zeros on there, but they should cancel out. Gives us 5246. So 5247, we're going to call it. Inches. Now I'm going to convert that back into feet by dividing by 12. 437 inches, basically. What does that mean? Well, that means is, what's that? That's going to be feet. You're right. Thank you, feet. And what that means is our beam, if you assume that this beam is the arc of a circle, that it's bending into a circular arc, the center of that circle, the radius of that circle, is 437 feet. Now, if we assume that this distance across here stays roughly that 12 feet that we had, we can use that to find the deflection here. It's actually not nearly as tough as it looks. We can drop this here. This would be 6 feet, half of the 12. This is 437 feet. This distance is going to be the square root of 437 squared minus 6 squared. So 436.9588 whatever. The difference between that and the 437 is our deflection here. So subtract 437. This just deflected 0.04 inches. Actually, 0.04 feet, that would be. And you have to multiply by 12 to make inches. So 0.49 inches. It just deflected. That's the tough part. I always have to make sure I'm careful. You get confused whether you're working in inches or feet. You got to be really careful with that. So this is deflecting just under ½ an inch is what we're getting for deflection off of this. Is that acceptable? Well, let's assume this is a floor. We're working at L over 360. 12 feet is 144 inches divided by 360. .4 inches is our allowable deflection, so no, 0.48, 0.49 is too much. So that is over the allowable deflection. Make sense? Yes. Oh, because this is in feet, 0.04 is in feet. So I just multiplied by 12 to turn it into inches. From the radius, yes. But the radius minus the height. But we're dealing with feet there, so you got to convert it back into inches. So this is telling us pretty much is that most likely the 10-inch deep beam is not enough here. We probably have to go 12 or 14 inches deep to make that work. This also does a great job of showing you the relationship between width and depth of a beam when it comes to deflection. Because right here, the moment of inertia, the width is in that factor once, but the depth is to the third power. So increasing the depth greatly increases the moment of inertia. Increasing the width just increases it slightly. And that moment, increasing that moment of inertia is what we need to do here in order to make sure this beam gets under that 0.4 of an inch of deflection. So that's a lot of work. Having to go through the arcs of the circle here to find that deflection is really kind of a pain in the butt. So fortunately for us, our textbook gives us some shortcuts. So we're going to take our break right now, and then we'll come back and we'll look at the shortcut formulas that the textbook uses to help us deal with deflection.